To finish up the year, our last couple lessons are going to be on the idea of sequences. Now, a sequence is a list of numbers that follows some kind of predictable pattern. So the most common sequence is the sequence with a bracket around the letter N. And what that sequence stands for are the numbers that go in what we would call counting order. So 1, 2, 3, 4, 5, etc. It doesn't start with 0, it starts with 1 and always starts with 1. So you know you're working with a sequence when you have bracket around the expression. Another sequence could be something like n squared minus 1. And so that would mean you would take all the numbers from the n sequence and you would square them and subtract 1 every time. So we'd start with 1 squared and we would subtract 1. And then 2 squared and we would subtract 1. And 3 squared and we would subtract 1. 4 squared, subtract 1, etc. Which would generate the sequence of 0, 3, 8, 15, 24, ... So the ... shows that this is an infinite sequence. It just extends on and on and on without ever ending. Another sequence might be something like 4 over n plus 2. So that sequence is generated by taking each of the counting numbers, starting with number 1, and plugging it in. So 4 over 1 plus 2. The next time the 4 stays the same, but we change it to 2 plus 2. And the next time the 4 stays the same and we change it to 3 plus 2. And the 4 stays the same and we change it to 4 plus 2, etc. So that generates the sequence 4 thirds, 4 fifths, 4 fourths, not 4 fifths. Let's get that right. 4 fourths, 4 fifths, 4 sixths, and we could follow the pattern and we would have 4 sevenths, etc. So the 4 stays consistent in the numerator, but you can see the denominator is progressing by 1. So these are different kinds of sequences. Now, if the sequence follows a pattern of addition, then it has a special name, and we define that. That is a definition, and we're going to define that as an arithmetic sequence. Okay, an arithmetic sequence. And the definition of that is that the terms are built with a pattern of addition. Now technically, addition. So technically, a subtraction pattern would fall under the category of arithmetic, because subtraction is really just adding a negative number. So as long as you're adding something, whether it's a positive number or a negative number, we define that to be called an arithmetic sequence. Now there are arithmetic formulas. And there are two kinds of arithmetic formulas. The first kind is what we call an explicit formula. That is where the sequence a sub n is generated by the following. A sub 1 plus d times n minus 1. Okay, those are subscripts right there. A sub 1 means that's where you put the first term. Okay, so that value right there is whatever number comes first in your order. D is what we call the difference between each term. It's what's being added, whether it's a positive number or a negative number. It's the difference between terms. And we already know what plain N stands for, that N stands for all of the numbers that count starting with the number 1. And so we would consecutively plug in 1, 2, 3, 4, 5 into that expression right there. So that would be plugging in 1, 2, 3, 4, 5, etc. So this is called an explicit sequence. That's not clear. That should be an N right there, A sub N. There we go. So that's one kind of sequence called an explicit sequence. There's also something called a recursive sequence. A recursive sequence also is following a pattern of addition, and its formula also starts with a sub 1, excuse me, A, but then a subscript is in minus 1, and then it's just plain old plus D. So that is how you write a recursive sequence. You write a recursive formula. So depending on what the question asks you for, you're just going to plug in to each of those. All right, so let's do a couple examples. Here is your sequence. -6, comma, -2, comma, 2, comma, 6, comma, 10, comma, etc. Now, at first glance, you should be able to tell that that is an addition sequence because the difference between each term is adding up the number 4. And so our explicit formula would be A sub n equals, now we start with the first term, and the first term in the list is -6, plus the difference between each terms is adding 4. So I'll put a 4, and then I put n minus 1. Okay, when I'm writing the formula, I leave the n as the variable n because a formula needs to have variables. It can't just be all numbers. You need to have some kind of variable, so n is your variable. Now, if I wanted to extend this formula, then I would start plugging in the numbers 1, 2, 3, 4, 5. So plugging in 1, 2, 3, 4, 5 would give me the terms that I have right now. Plugging in 1 would give me -6, plugging in 2 would give me -2, plugging in 3, plugging in 4, plugging in 5. And so the advantage of an explicit formula is that you can jump way ahead down the list. Say I needed to know what the 17th term in the list was. Okay, so if I wanted to find the 17th term, well then I have -6 plus 4, I put the number 17 in, and then I can evaluate that. I don't have to waste my time going in order all the way up to the 17th term. I can just evaluate, oh, well, that's -6 plus 4 times 16, that's -6 plus 64, which turns out to be 58. So the value of the 17th term in the list is number 58. I can jump forward to the 100th term or the 101st term. Okay, I don't have to go in order. I can jump around finding the values of the different terms. Now a recursive formula for this same example would be written this way. A sub n minus 1, remember we need to have our variable, plus the difference of 4. Now the limitation of a recursive formula is that you have to be told what the first term is. And the first term is going to start you out at -6. And so you're told both the first term and the difference in separate lines. Okay, the plus 4 is the pattern, and then you start with a number of -6. The downside of a recursive formula is that you have to go in order. If I needed to find the 17th term, I would have to find all 16 terms coming before that to get to the 17th term. There'd be no way for me to jump around and jump ahead. So a recursive formula isn't usually the most desirable because It doesn't allow you to jump around in the sequence. Okay, let's try another example. All right, let's suppose the sequence was 17, 14, 11, 8, 5, dot, dot, dot. Again, hopefully you can identify, oh, that is adding -3 every time. Don't say subtract 3. Okay, always reference it as adding something. And so we write our explicit formula for this. So bracket a sub n equals the first term, which is 17, plus the difference, which is -3, times the parentheses n minus 1. And using that explicit formula, again, you could jump ahead to any term in that sequence by plugging in the number of the term you want to find. The recursive would be written as a sub n minus 1 plus the difference of -3, and the first term starts with 17, so you would write it that way. Okay, one more example in this little set. All right, suppose that you know that the second term in the sequence is 3, and if you jump ahead to the fifth term in the sequence, it's 24. And you're asked to fill in the gaps of what the sequence would be. So this one's a little trickier. Just you got to really put your thinking cap on here. If you have to figure out the common difference yourself. And so you're going to set up a system of equations. We know that the explicit term would be that a sub n is a sub 1 plus the common difference of d times n minus 1. Unfortunately, I don't know a sub 1, and I don't know the common difference of d. So I got to work with what I've got. I know something about the number 2. So if the number 2 is put in for n, even though I don't know d and I don't know a sub 1, I should end up with a value of 3. I also know something about the number 5. If I put in the number 5 for n, even though I don't know d and I don't know a sub 1, I should come out with the number 24. And this is a system of equations that you could solve with elimination or substitution or any method that we've been working on in this entire unit. So it's like we've come full circle back to the very first day we went on. We started this unit. After our trig chapter, we started this, and now you can, let's do elimination. So let's say 3 equals a sub 1 plus, and let's distribute the d. So that would be plus 2d minus 2. And then 24 equals a sub 1. Again, I'm going to distribute the d. So we now have 5d minus 5. And if I multiply the top row by -1, I'll have -3, negative, negative, and that turns into a positive. And I can eliminate. And what eliminates is the a1. That leaves me with 21 equals 3d minus 3. I can add 3 to both sides, so I get 24 equals 3d. And now I've just figured out that the difference has got to be 8. So the difference between the terms should be 8 every single time. Now can I use that to help me figure out what my A1 is? Sure, I can go back and plug that into either of the equations. Might as well just go with that one. So I'll say 3 equals A1 plus D, which we know to be 8, and then times 2 minus 1. So that's 3 equals a sub 1 plus 8 times 1. Please excuse my dear Aunt Sally, parentheses first. Subtract 8 from both sides. So a1 is negative 5. And so our explicit formula must now be a1, which is negative 5, plus the common difference of 8 times n minus 1. And that explicit formula will allow me to jump around to any other term in the equation in this sequence besides just the second one and the fifth one that I was given. Now I can find any term in the sequence at all. Another thing you might be asked to do with arithmetic sequences is to find their sum. We write sum like this in Greek. That is the Greek letter sigma, and that would be written like this. That would mean take all the numbers in the sequence and add them up together to get a single number. And so an example of that might be something like this. If a sub n is 7, oh, that wasn't very good, 7, 9, 11, 13, ... and ends with 55, then find the sum. So in other words, add them up. Now, the long way, although it's the easy way, would be to simply grab your calculator and spend some time adding up all those numbers. So say 7 plus 9 plus 11 plus 13, and you'd have to figure out all the numbers in between and go until you stopped with 55. So you for sure could do it that way. If you don't want to learn the shortcut and you just would rather do it the long way, more power to you. However, there is a better way. So first we'd want to write an explicit formula for this. And so we can tell that the common difference is 2, and the first term for this sequence is 7. And so I would say 7 plus 2 times n minus 1. Using this explicit sequence formula, we want to know how long this sequence is. Okay, it goes all the way to 55. Now, how long is that? So if the last number is 55, what n goes with that? So we want to solve. We want to multiply or distribute our 2. So that'll be 55 equals 7 plus 2n minus 2. In other words, 5 plus 2n equals 55. Subtract the 5 from both sides. 50 equals 2n, so n is 25. That means there are 25 terms in the original sequence. All right, from beginning to end, there were 25 terms. And so that will help us with the shortcut of figuring out what the sum of this is. And the shortcut is this. You take the first term, a1, you add it to the last term, which we indicate as a sub n. You multiply that by n itself and divide the whole thing by 2. So let's see if that works for this problem. If we want to find the sum of the sequence that we just did, we take the first term, which is 7. We add it to the last term, which is 55. We take n, which we discovered to be 25, and we divide the whole thing, I can write it like this, by 2. Okay, well, let's see what that turns out to be. 7 plus 55 is 62 times 25 over 2. Now, before I do the multiplication, I usually like to reduce if I can. So I'm going to reduce 2 into 62 and get 31. So I'm left with 31 times 25. So I get 775. So if I had added up all the numbers by hand, I would have gotten 775, or I can use this shorter way to also get 775. So you decide which way works for you. The longer the set, the longer the sequence, the longer it's going to take you to do it by hand, and the faster it would be to do it with the shortcut method. The shorter the sequence, and if the sequence is super short, then you might as well just add them up. Okay, if there was only 5 terms in the sequence, then I would just add 7 plus 9 plus 11 plus 13 plus 15 and be done. But because there are 25 terms in the sequence, it's probably a toss-up as to which method was faster for me, okay? All right, so you've got sequences, you have ways to make formulas for them, and you have ways to add them all up. These are for specific, and this formula, by the way, only works on arithmetic terms, okay? It doesn't work for every one. It's only good, the formulas I've given you today, they are only good for arithmetic sequences. So if the pattern is not, if the pattern is not arithmetic, if this is not an addition or adding a negative number, then these formulas are no good. I will give you some more formulas tomorrow for some other situations, but make sure you're only dealing with adding positive or negative numbers.